Okay, so now we're going to go over series. So series are like sequences, except we're using all those sequence terms added up. It's the summation of all the terms in a sequence. So we're adding up summation of the terms in a sequence. And we're going to introduce some new notation here. So this is called sigma notation. This is a shortcut way to write addition out. So the way this looks is you use the Greek letter sigma. That's why it's called sigma notation. And it looks like a really fancy capital E, like this. And then we have a few things around this. So below it, usually you have something that looks like this. Above it, you have something else, another number. And then off to the side, you'd have some sort of equation. So let's put this. Like limits, the equation should be in parentheses to mean that that whole equation is related to the sigma. So what does this mean? This tells us the sigma, the fancy E, tells us that we're summing up things. So it's saying take the sum off this sequence that's defined by this formula. So this tells us the formula for the sequence. So use this sequence and take the sum of it, starting with the first term when n equals 1. So this is called an index. It tells you where to start. And then stop when you get to n equals 20. So that's the stopping value. So this would look like, well, you'd have to take the first term, so plug in 1, and then add it to plugging in 2, and then add it to what you get when you plug in 3, and so on. And keep going until you get to plugging in 20. So instead of writing all of that out, we can write it in this more simple sigma format that's more concise. But it means all of this addition over here, which is a lot of addition. You can do some operations with sigma notation, but we're not going to focus too much on that. So I'm going to just leave that out. You don't need to know that for now. What I want to show you with this, kind of related, slightly different, is factorial notation. So sigma gives us this nice way to do multiple addition things. Factorial gives us a nice way to show multiple multiplications. It's not the equivalent of sigma for multiplication. There's another thing for that. But this is also going to be important later on when we do induction proof. So I'm going to show it to you now, just so you know what it is. It was also in that packet. So factorials, for example, n factorial. Right? So this factorial is this exclamation sign. It means that you take the number over here and then multiply it to the number before it, and then the number before that, and the number before that, and keep going until you get to 1. When you get to 1, you stop. So for example, 5 factorial would be 5 times 4 times 3 times 2 times 1. Nice stop. Right, so it's a way of writing out this particular kind of multiplication where you have to multiply down all the way in a concise way. It doesn't let you vary the sequence on this. Like the sigma notation, you can put any equation in there and it will, for what terms you need to add up. Here, it's very specific on which terms you're multiplying. You're just starting at the number you're told and then keep multiplying one less than it each time. One special thing with factorials is when you have 0 factorial, that is defined to be 1. It works out, it makes the math work out for a lot of things, but it's kind of weird. It's not the most intuitive thing that, like, if 0 factorial would be 0 times something, which should just be 0, but it's actually 1. So that's the main thing you should know about factorials. Similar, in the same vein of doing concise notation like sigma notation is doing, but it's a very specific case of it with multiplication. The last thing to do with series is from sigma notation, now you have all these terms that you need to add up. Now you could sit there and like calculate every term and add it all up, but we also have some nice formulas that people have come up with, looking at these patterns to come up with formulas to add all these things up. So we're going to look at specific formulas for series that have arithmetic sequences and series with geometric sequences, there are a lot more formulas out there. There's a lot more out there with sequences and series. If this is your end of year assignment, like this is the topic you want to do, I would highly encourage you to go look at all those additional things. Even with these formulas, I'm going to show you the formula, but there's some really cool interpretations you can look at for why these formulas work, how you get them. There's some really nice geometry stuff you can do with this. So that could be some really cool things that you look into if you're using this topic for your end of year assignment. So real quick, the formulas for an arithmetic series. So this is a series that is defined by an arithmetic sequence in it. You can only add these up if it's finite, meaning it needs to have an end on it. If it doesn't have an end, it's going to go to infinity or to negative infinity, right? If I'm adding up numbers, like, let's just say like this sequence of numbers, 1, 2, 3, 4, 5, etc. If I keep adding them with no end, well, it's not going to equal anything. It's going to be infinity. It's going to go really, really big. So you can only add up arithmetic sequences when they're finite. The equation for that, so the sum of n terms, is you take whatever number of terms you're adding up, take the first term, add it to the last term, and divide it by 2. There's a lot of different ways you'll see this written out. The way I've written it out is how I intuitively think about this formula geometrically. You can kind of see there's this sort of average idea that I have. I've taken the midpoint over here from the first term to the last term and divided it by 2. That gives me the center of it. And then I multiplied it by the number of terms. That should give you a hint for where this formula comes from. But that's the formula for it. And I'll do an example with this later on. For geometric series, so again, we can add it up if it's finite. So when it's finite, you take the first term, multiply it to 1 minus r raised to the number of terms that you have, and then divide it by 1 minus r. Again, if you want to see why these formulas work, that could be a cool thing to do in your end of year assignment. Or you can ask me and I can show it to you if you're interested. But I want to keep this video just small, short, to just the main points that you absolutely need to know. But with geometric series, the cool thing is you can also do infinite sum additions. So this is where the sequence goes on forever, right? You can keep adding more terms to it, but you can add it. And we can do that because of this calculus stuff that we've learned about, all this limit stuff, the asymptotes, things approaching values. So if we think about this formula, supposing I have n as infinity, right? I'm adding up a bunch of n's. Well, if I have an r value that's bigger than 1, right? So 1 minus some big number raised to the n. Well, this is going to get really big, right? A big number raised to another big number is still a really big number. And then 1 minus that is going to be a really big negative number. So this is going to be really big. If r is greater than 1, this is going to do the same thing like that arithmetic series do, and it's going to go to infinity or negative infinity. But now imagine if we have a really small number. If we have a number that's less than 1. Right, so if I have a number less than 1, right, so let's say it's like 0.3 raised to the n. Well, in this case, when I have a really small number raised to a big number, it just gets closer and closer to 0. Right, if this is like almost infinity, when n approaches infinity, a number smaller than 1 raised to it is getting closer and closer to 0. So 1 minus 0 is just 1. So this whole term goes away. If you have an infinite series, that 1 minus r to the n just becomes 1, so we don't need to write it. It's just this bit of the formula. This only works if your r value is less than 1. The absolute value of it is less than 1. Hopefully that makes sense on why it only happens when it's less than 1, right? It's that same idea that we looked at, especially when we looked at rational functions and exponential functions, all these functions where you have those asymptotes, you're getting closer and closer to 0. The reason we're getting close to 0 is we have a small number raised to a really big number. So let's do some practice problems with this. So the first one, we're just going to play around with sigma notation a little bit. So here it gives you sigma notation for a series. We want to write it as the sum, just to make sure we understand what sigma notation is doing. So this tells me, take the sum of the sequence of numbers that follows this pattern, start at n equals 1 and go up to n equals 4. So I'm going to start at n equals 1 and then keep going until I get to 4. And then I can evaluate that. So 20 minus 1, 20 minus 4, minus 9, and minus 16. Right, this is the sequence. This is the series that this notation is describing. And then this would equal 15 plus 16 is 31, 31 plus 19 is 50. And let's do the opposite. So here we have a series written out. We want to write it in sigma notation. So we're going to write a sigma. Usually we start at n equals 1. You can start this anywhere you want, but your formula would change based on that. So usually I do n equals 1. And if n equals 1, well, I can see the pattern here that every numerator is a 1. So I'm going to fix that. That doesn't change. The only number that's changing is the bottom number. And those are all powers of 3. It's 3 to the 1, 3 squared, 3 cubed, 3 to the 4. So I can write the bottom as 3 to the n. And I need to go 3 to the 1, 3 squared, cubed, 4, 5, 6. So I need to go up to 6. That would be my sigma notation for this. Hopefully still pretty straightforward. Now we'll get to evaluating the series, and here we can use some of those formulas that we have. So this is like the condensed sigma notation format. What it does if I don't put it all on one line, really this is saying k equals 0 on the bottom, 5, 20 minus k. So here's an example where we don't start at 1, we're starting at 0 instead. So that just means that the first term in the series is going to be when you plug in 0 instead of plugging in 1. And then you're still going to go until you plug in 5. Now, instead of calculating this, we're going to use the formula for it. This is an arithmetic sequence formula. It's just a slope, right? Minus 1 every time, start at 20. And for that formula, if I look here, I need the first term, I need the last term, and I need to know the number of terms. Well, the first term is 20 minus 0, which is 20. And the last term is when I plug in 5, which is 15. The number of terms is 6 because I have the 0, 1, 2, 3, 4, 5. That's 6 terms. Right? So when you start at 0, it's not 5 terms. When you start at 1, it would have been 5 terms. So now I can plug all of this into my formula. So sum with 6 terms is 6 times 20 plus 15 divided by 2. Well, that's 3 times 35, which is 105. Let's do some looking at when we change that index value. So here, this sigma notation starts at 5. We want to make it start at 1 instead. So this is fairly straightforward, but it looks kind of confusing sometimes. What you're doing is you're changing 5 to 1. So when you make that change, then the top number also has to change. Well, we reduced this by 4, so this would also have to reduce by 4. So that would go up to 7. So you need the same number of terms. From 5 to 11 is 7 terms. So from 1 to get to 7 terms, you need to go to 7. Then the formula also has to adjust for this. Since we went down 4, well, I need to make sure that the number I get when I plug it in is the same number. So for example, here when I plug in my first term, I get 5 plus 400, I get 405. But over here, if I plug in 1, I get 401. I need to get 405, which means I need to add 4 back, right? So I'm subtracting 4 here, but I'm adding the 4 there. It's kind of like when you solve equations. You need to keep it balanced. Right? You subtract something, you add it to make sure that it's still equal. That's what we're doing here. So I'm adding 4 to adjust it, and I still have my formula. So cleaned up, this will look like m plus 404. So that's just a little bit on the manipulations of sigmas that you can do. You can change indices on sigma. It would just affect what the formula looks like. Same thing here, if you want to start at 3 instead. So then I'm adding 2, so then that goes up by 2 as well. And then since I added 2 there, I need to subtract 2 here. Make sure the variables match. So if this is n and n, this was m, so I need to make this m. Okay. Last few problems. Again, we're going to evaluate some series using the formulas we have. So looking at this one, this is an arithmetic sequence because it has a starting value, it has a common difference here. So I need my first term, last term, and number of terms. Well, the number of terms is 6 because I start at 1 and go up to 6. My first term is when I plug in 1. So 9 minus 10 times 1 is negative 1. And my last term is when I plug in 6. So that would be 9 minus negative 60, which is negative 51. Then I'm going to use my formula. So this is sum of 6 terms, which is 6 times first term plus last term divided by 2. So this would be 3 times negative 52, which is negative 156. Next one, we have a geometric sequence now. It's multiplied. For geometric sequences, I look at the r value. R is 1/2, which is less than 1. So I know I can still sum this up even though it's infinite. For that, I need the first term, which is 2 times 1/2 to the 1, which is 1, divided by 1 minus r. So this is 1 over 1/2, which is 2. So look at that. This infinite series just equals 2 because all you're doing is you're going 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 and so on. So these numbers are getting smaller and smaller and smaller that like this is already 1.5. This is 1 3/4. And then the last quarter is going to be all of these terms added up. Because these terms over here are so close to 0, it's really not making a difference. That by the time we're about here, we're already like 1.99, and it's just going to be 1.999, and then 1.99999 until you eventually get to 2. Let's do this last one. This is a bit of a challenge. So we have this series to write in sigma notation, which looks fairly simple. If this was 1/2 plus 1/4 plus 1/8 plus 1/16, you can see the pattern really quickly. Right? It's 1 over 2 to some power. But now we have these minus signs every so often. So I want you to think about how would you incorporate the minus sign into your formula so that it alternates to a negative sign. So I'll give you the answer in a bit, but think about it first. Pause the video, think about it, and I'll show you how to do that. So starting off, I give an n equals 1. Simple to start off with n equals 1. And I know I need to go to 6 terms. And I know it's a 1 in the numerator. That doesn't change. In the denominator, I have a 2 to the n. I know that happens every time. But I needed to alternate between -1 and +1. There's a few different ways you can do this. A very popular way is to multiply whatever you have by -1 to a power. So if I multiply the -1 to the n, well, if I try that, if I plug in 1, I get 1 over 2 times -1. That would make this first term negative, but the first term is positive. So that's not going to work. But notice that this -1 will change the signs. If I do it this way, I'd get -1/2, and I get +1/4, and then -1/8. So I'm getting basically this, but the opposite. So the other thing I could do is just make this negative, and then that will always make it the opposite of what it already is. Or I can add 1 up here, and that will also alternate the signs. So it's really just a matter of manipulating some exponents around to make these signs work out. Hopefully you were able to see that. or at least see why it works now. Many different ways to do this. This is not the, I mean, yeah, there are so many other ways I could write this. This is one easy way to do it. So hopefully this was good review on sequences and series if you needed it. And then you can move on to looking at some of the induction proof videos.